Okay guys, today we will speak about two different algorithms, and this is our final class. And if we see here, we have well, this is not that. I need to open the data structures and algorithm course. So we have to speak about genetic algorithms and Dijkstra algorithms. So the first lecture we will take genetic algorithms, and then we can speak on Dijkstra algorithms on the second lecture. So genetic algorithms are interesting because they are used in different fields like machine learning, artificial intelligence, and somewhere where we need to make some decisions. And in order to start genetic algorithms, here we have to explain. You see here I have put the task, so please download the task, genetic alg task, and then we will start to discuss it. So genetic algorithms are a part of evolutional algorithms. And what is evolutional algorithm? It is such a special thing when you have to go through some evolution stage.
Hello, excuse me, sir.
Yeah, what?
Can you share your screen?
Yes, I will share my screen. Yes, one moment. We are speaking about genetic algorithms. So genetic algorithms are a part of evolutional algorithms. And evolutional algorithms, they are made so that they look for different solutions by making different stages. And first of all, let us try to remember what about genetics. So let us try to remember genetics. And do you know what genetics is? Genetics is a kind of a biological science. But maybe you can ask, what is the meaning of biology in informatics and computer science? Yeah, but here we have special algorithms which try to create a different kind of solutions. For example, now let me start the algorithm first, because it's better if we just have again the practice. So here, as I opened the program, which I also uploaded to Moodle, you can meanwhile parallelly open it. If you have some problems, you can tell me and we can share your screen, and I will guide you how to negate the problem. So here you have to start the simple demo genetic algorithm. When you start it, it's gonna be working like that. Let us try to see what is being done there. So you can see here we have some kind of results. And here we have generation 0, fittest 5, solution found in generation 0. So this is like that. Now let me end solution like fitness 5 and genes 1111. Let me do it once again, because this algorithm is very simple. It is made for tutorial purposes, and you can see here now you have a solution found in generation 2. So it means that now we have generation 2. If we just make once again, you can see now the solution is found in generation 3. But if you launch the same, for example, Roman, if you launch the same now, you can have totally different results. I will explain why. Because here you can see the solution found in generation 14. Yeah, so it means that here you have a lot of different kind of approbations, and finally you have found. And we can stop here and we can analyze what is written here. You see, so here we have generation 0, generation 1, generation 2, generation 3 up to 14, and here you have the fittest option, some kind of what is the fittest. We will speak about that. It is firstly 3, then it is 4, 4, 4, and then it is 5. So what is there? And here we have the solution found in generation 14. And what I want to say is that here genes, you see genes are now 1, 1, 1, 1. So basically this program, it is looking for optimal solution, but if you see how the program is written, let us start to find the main class where we started. So here we have simple, and we have to see where they have the main idea. So most probably it is somewhere here. Yeah, you see here public static void main. So what we do, let us start to analyze what we do in the task itself. And if you open the program, you can see firstly you create a kind of a random object, then you create a new class, and then you create a kind of a population. Then you have to calculate the fitness, then you have to write something, and here you perform the cycle, etc. But in order to understand this, I probably try to sketch up what is this. Genetics, what does it mean? Genetics and generations. I guess you know all these words. What are these? Do you know what word generation? It is like we are generation. Yes, you are younger. Yes. Hello, I am a little bit older, and we represent different generations. And after people die, the new generation become like adult, and then so on. And so we are just changing generations, and we live in on this planet for many, many millions of years. And generations also are important in genetic algorithms, because what we do, we just try to make some kind of similarity to what happens in biology. In biology, you know, we have generations, but in one generation you can have a population. Do you know the word population? So, hello, yes. So what does it mean, the population? How do you think, guys? What does it mean, population? Amount of people, yeah. So basically population is amount of people, and we have a country, we have, for example, in Lithuania there are many people, in Latvia, in India, in Estonia, yeah, so we have population. And the population, actually human beings, they have certain amount of living time, and then they die, and then the new generation come, and then again they have their life, then the new generation come. But if we speak on the human population on Earth, it is existing for thousands of years, because we all the time produce the copies of us. But if we speak about the genetic algorithm also use the same principle. Like if you look on the living creatures, they have generations, populations, and what is the meaning of our life? We want to reproduce ourselves, and we want to become better. Because if you see, actually what we have some kind of information, genetic information, which is given to the first human beings, and now we are carrying this information forward in time. But every time we make children, the children are, yeah, they are different, and they are taking some information from both parents. Yeah, so for example, from father and from mother, the child takes some information, but we cannot determine the way how the information is taken, because it's taken basically randomly. You can take one gene from mother, one gene from father, and it depends on dominating gene or not dominating gene, but actually the human being becomes another creature, another character, another look, etc. And actually this is the evolution, because if we look into very, very past things, then probably we were not so perfect, because we had some like we were, if the person from the ancient era would come to our world, maybe he would die immediately, because here are some different viruses which already have evolution, and they can kill the person from yeah, so and etc. So all the time we are learning something, and we are improving ourselves. And in programming, in computer science, genetic algorithms, evolutional algorithms, they also do just want to follow the same principle, that if you have to solve a problem, you need to offer the initial solution to solving this problem. But this solution is not perfect. Do you understand it? The solution is not perfect, but you can make it better. You can make it better by changing something in the solution. But we can do like that, so we can do like this, that we can have one solution and one more solutions. We have like two parents. There are two solutions, and we can have not only one or two solutions, we can have 10 different solutions which are offered, for example, in the beginning. And we can scan each of the solution and estimate how perfect they are, how well they represent the solution of the problem we need. And we can choose two best candidates and see how those candidates solve the problem. If they don't solve it perfectly, we can try to get the information what is in the candidates, and we can cross over. You know, crossover means like when the when the mother and father come together, they make a child. So this is a crossover, basically. The process which is happening on the microbiological level, where one chromosome and another chromosome interchanges, this is the crossover. And it means that we have to model something similar to the problems which we want to solve in computer science. For example, we want to translate a sentence and we want to make it perfect. So we can have different translations, and then we can launch an algorithm which will improve those translations. We can have some kind of function. We have the data, for example. We have a lot of data and we want to build a function. For example, we have a data for some kind of financial things like stocks value on the market starting from the last year until now, or some kind of Euribor rate at something. And then we can have the data and we want to set a forecast what will happen afterwards. So we need to represent the data and we have to build a function which is going to draw how the Euribor, for example, grows or decreases. And then we can make some kind of function approximation and forecast what will happen. And then we need to build the function. But the computer can build the function by making some kind of different things, because you can have a lot of different primitive functions putting all together, and then you can build another function which is like that. And or you can do another case. So there are so many different opportunities to create some kind of solutional problems. Yeah, but also, and then we have to build a population from the initial solutions, and we need to improve it, and then as soon as we improve it, we create new generation, and so on. And then the new generation we can scan for maybe there is a perfect solution for our problem, and so on we go. Do you understand that? Yeah. And the same is implemented in genetic algorithms. I want to say that in genetic algorithms we also have generation, we have the population, and we have the so-called crossover. You know, crossover, it is like when you just interchange the genes. Then you can have mutations. You know what mutation is?
Mutation?
Mutation.
Some sort of change in the genetic
Yes, yes. For example, there is a genetical information of the human being or of the human creature or of the creature, and if the mutation happens, then one gene can suddenly change the value. And it means that when you have mutations, then you can also make yourself better or worse. Yeah. Sometimes mutation can bring some diseases to the organisms. Yeah, sometimes it can be more healthy. For example, it can be more resistant to viruses, etc. It depends on what kind of mutation has happened, and the mutation can happen randomly. It can happen totally randomly, or and so on. So you cannot affect it, or it can be because of some radiation or something like that. So it depends on what. But we need to, in order to solve genetically the problem, we need to understand how this algorithm works. If I back return to my soft, you can see here we have run this program, we have run this software, and here is the result of what the software has done. And you can see here, we can see generation 0, fetus gene was 3, generation 1, fetus gene was 4, generation 2, fetus gene was 4, and so on and so on, and then generation 14, fetus gene is 5. And then we can say the solution found in generation 14, fitness 5, and genes. So here in this program, in this code, it is made so that initially you have a kind of population. You can have a population of 10 different genes. Yeah, do you understand? You can have a population of 10 different specimen, and they have the sequence of 5 genes. Like, for example, this could be the example of the genetic information of one specimen.
Yeah.
And you can see, as we use binary thing, we can use 0, 1 in one gene. It means that in this gene we have the value 1, in this we have the value 0, here we have the value 1, 1 and 1. It means that if our aim is to receive that all the genes have the value 1, in this example, yeah, and in this example it has to be value 1, so then we can generate the population which corresponds to different kind of specimen. And when we generated the population, we can see that, and so on. So now we can try to debug the program, and we can see how it works. You see, I can run it once again, so several times. Hello guys. So here, for example, I can run it again. You can see there will be totally different solution. Now it is enough to find solution in the 4th generation. If I launch it once again, it can be at once you have the solution. You can see. So it depends on what is the random situation. So here you have the generation in the solution in the 2nd generation, in the generation 1, etc. So it depends when you run. So here you have the solution in generation 4, so 5 generations has to be changed. But let us try to see what will happen when you do the soft. So as we found the first main method, we can create a debug point here, so we can create a breakpoint, and we can start debugging process. So if we start debugging process, you know what debugging is. So here is the piece of code what we need to take, and you see here now we are located exactly to the first line, and here you can see all the values what are there. So if we execute this line, we will just make a random object. You can see we have created the object which is called Rn, and at the moment it is totally empty, but this object actually represents some kind of random generation, so you have generated the seed number in order to get the random access numbers afterwards. So this is not interesting, so we can go forward and we can go to step over to go to the next line. And now we create, you see, the demo population, and here we have initialization. We have initialized the special class of population, and you can see how in Java it is programmed. So if you make control, you can say, you can make the you see here it is demo population, and here we need to see, here we have simple demo. So basically now I have generated a demo. You see, I have generated a demo object which is on the class simple demo genetic algorithm. And you can see that simple demo genetic algorithm, here is the public class, you can see here, yeah? And this public class is basically containing several interesting situations. You have the population class, yeah? You have the individual class, and you have the individual, and here you have the generation count. So you just count what the generation is. And you can see that here there are 2 classes defined, what is individual and what is the population. So we can go for population first. If you can open this class, and you can see what happens to this class. So here what we have basically individual class in population class, and in population. So if I open the population class, if I open the population class, so here let me see the population class. So here I want to see that I will open the class population, and we see what is inside the population. So we have the population size, it is 10. What does it mean? That if we create a kind of a population, we just create 10 different species. Do you understand? Then here we have individual class. So what is individual? So if you open the individual class, you can see individual, it is a clonable thing. So here basically it is a special kind of clonable interface, but individual, we will just create a one person which can be could be cloned, etc. And you can see that individual class, what you do, initially you set it fitness 0, and you get the genes for individual. And you can see that the genes basically represent the one-dimensional array, and they consist of 5 different elements. Is it clear? So 5 different elements, and you can see if you put the population, you can see the population size is 10, and individuals, at the moment there are no individuals, but we are going to generate them. Yeah. So let us see how it is generated. So if we return back to our algorithm, so we have done here, we have created a demo, which is simple GO, but which consists of population object, yeah, individual fitness, fittest object, and second fittest, because we need to choose 2 individuals from the population to make a crossover. And here you have the population, here you have the fittest, the second fittest, and you have the generation count. This is you just created the demo. You see, you have created a demo object. Demo is the object of the class simple demo GA, but simple demo GA class contains the following instances, the following attributes, and those attributes are generated. But at the moment they are only generated, but they don't have any values there. Understandable? Yeah. And it means that now we have to initialize the population. You can see demo population initialize. So we just take this object which we created, we just make the function population and initialize population. So if we go to population, you can see this is the population object. Yes, so we take the population object, and what is the population object? You can see, you know that the pop size is 10. You have some 10 individuals which are not generated, and the fittest at the moment is 0, so we don't have anything what the fittest is. But if we go here, we can say the method initialize the population. You can see what happens. What will happen in order to initialize the population? We see the individuals. We don't have individuals here, but we see the pop size here, and you can see the individual population. Here we have size. But if we go to our genetic algorithm here, the beginning of our genetic algorithm, you can see initialize the population of 10. So what does it mean? We will make 10 different specimens. Understandable? So we make 10 different specimens, and after we create this, we will see, here we will have the 10, and what we do, here we have initial population, we have a cycle from 0 to 9, so we will generate 10 elements, and you see individual of the order number, it will be like new individual. But if you want to see what is new individual, and you can see if you want to create an individual, we have to make a random number, and now what we do, we take the maximum of gene length, but gene length is equal to 5, so we generate the 5 genes. Yes, so here, and here you can see they all the time divide the randomly generated number by 2 in order to get so this is mod 2, so they get the rest, the residue 0, 1, and then look, if you do like this, you will generate 10 different populations. Let's just execute this. I can go here. I can go here. You see, I'm now executing this random population. Look what happens. At the moment, you don't have population defined, so you don't have individuals here. It's null. You see there, yeah? I hope you see. If you don't see, I can lift it there. You can see individuals are null, so you don't have any individuals here. But now I'm going to generate the individuals, so I will execute this one. You can see I'm now executing, and you can see I have already 10 individuals. 0, 1, 2, 3, 4, 5, 6, 7. You see? If you open individual 0, you can see fitness is 0, and genes, you can see that 5 genes are generated for this. Do you understand? The 5 genes. This is randomly generated. Do you get it? Yeah? So what we do, we just make 2 different. And now I want you to understand how it is implemented in Java, because it is good to see the implementation, how it is done. And you can see here, the second individual is located like that. Then the third individual is the following, and you can see that individuals can have only 5 genes. It is very primitive individuals, yeah, because how many genes are in human being body? It's about 1 millions of that, yeah, millions of genes. But here we have only 5 genes, so we don't have a lot of information. But because it is for educational purposes, this algorithm is for educational purposes, and you can see that initially you can generate a population with 10 different individuals, but individuals can have good and bad genes, let's say. So in this case 0 is a bad gene, but 1 is a good gene, and our aim is to receive an individual which has all ones. Do you understand?
Good genes.
Yeah, all good genes. So we need to make the perfect individual. And we need to see how we do. So firstly, we generated the first population. We generated 10 different 10 different objects, no, living creatures, let's say so. Yeah? And now we will need to choose 2 best ones, one the fittest and the second best ones. Then we will make a crossover with them, because it's like man and woman, and they make a crossover, produce a child, yeah, or something like that. So we will have to unite together 2 individuals, then we'll make a crossover, and then this child will substitute the worst individual in the population, and we will receive a new population. We will scan for the 2 best individuals. Again, we will make crossover, and again we will substitute the child by we will take out from the population the worst, the one which has a lot of zeros, and place it the new generation there. And all the time it will be like this. Yeah, so it's a kind of, but our aim is to get the individual which has all the time 1 1 1 1. Yeah. And you see, that is why when you launch this algorithm first time, second time, you always get different results, because you can have randomly chosen individuals in the beginning. Do you understand? Yeah. So you can try to launch it once again, and so on. So I want now you to understand how this is done step by step, how we generate the individuals in Java. So I will stop this program. You can see I can launch it again. When I launch it, now I have received my perfect individual. You can see this is the perfect individual. We have all the ones in genes, yeah, and it was received after 2 crossovers, because initially we had generation 0. The best individual was there with 4 good genes. Then we made a crossover. We received the new generation, and the fittest individual again still remained with 4 good genes. But then afterwards we again chose 2 best individuals, made a crossover, and finally received that it is best way. It is like 5. It's a perfect thing. Do you understand that? Yeah. And you see, this algorithm all the time creates this, represents this biological production algorithm. So you generate individual, you make crossover, you can make some mutation there also, and we can see it in the code. And later we will produce the generation again. Understandable? Eh? Yeah. So this is actually, this is the very simple algorithm for genetic 1, and in Java. In Python there are also some different libraries, but this one is very simple and we can just go through. So first of all, let me again, I have stopped here as a random. Let me again try to launch it, and we will see now step by step these 3 steps when we generated individuals. I want you to see how it is done. So first of all, when I launch it debug, you can see that now what we do, we just create a random object. This is the first, because we need to make the randomization. So this one is clear. I think we just can skip it. And now we go to the next line, this line. You see, random object is created, but this line, what does it do? It will create the demo object of the class, what is the name of the class? demo object. You see here is written demo, but what is the name of the class to which demo object belongs? How do you think? Look at this line. There is everything written. What is simple demo GA? Yeah, this is the class. This is the Java class which we defined ourselves. Now let us, if we want to see the class, you can press Control button and hold it. And then you can move the cursor on the name of the class. You can see. And if you want to read about the class, you can find definition of that class in the code. Just press on this with the left button, and you will be taken to the place where the class is defined. Sometimes the class is defined in the same file, but sometimes it can be different. Yeah, for example, when you work in big projects in Java, you define classes for each of the objects. For example, when I was working for with this project which I told you about, the POS terminal, we had the class for one card, for another card, for different things, etc. There are so many classes. This project is huge, and here you can always see this is the main class, simple demo GA. You can see it is before the main method. So this is the main class, and now here we define some basic things about this class. You can see here we make population of that class. Yeah, hello. Yeah. We have individual. This class has some kind of individual thing, some population, some individual one more, and so on. And you can see that here we have a population class, but this is the name of the object which is contained in the class. Do you understand? And you can see here fittest and second fittest and generation count. So there are 4 objects which will be generated for the object demo. Because we have created the object demo. Here you can see we have created the simple now. Now we are going to create it. And when we are going to create it, you can see that this demo will be, and here we can see this is like starts here. When it finishes here. And here you have only selection, crossover, mutation. We have methods, and here we have individual, get fittest offspring, and we have some kind of one method, another method. We have different classes, and here we have individual class represent, and here we have basically other things. But here we define the class simple demo GA, and we make an object of simple demo GA. And when you make this object, you can see now we are going to generate the demo. Now I will press the next line. This line will be executed, and look what will happen. So here now I'm just executing it. You see now we have 2 objects. Now I'm pressing. You see we have demo here. Do you see that? Yeah. We have demo, and you can see that here what we have population, yeah, we have fittest, second fittest, and generation count. It is totally the same what we have defined here. Do you understand?
So demo contains the population individual.
Yeah, demo object contains there all the information. Yeah, so remember, like we spoke last week about JSON. So in JSON you can place a lot of information, but here we don't have any kind of JSON. We just have an object, and this object will contain everything that we will define for the class. Because in Java we operate with classes, so we can create a different object. You will have object-oriented programming afterwards. You will make it more deeper. Yeah, but here I'm just explaining. My task is to explain the algorithm. But as we go inside, let us analyze. This is interesting to analyze how it goes and what is there. So it's always interesting to see what happens in the code. And you will never understand what happens in the code unless you debug. And this is always you do. So you see what I'm doing. I'm making the breakpoint, and I'm going step by step through this. I always do like this when I had to solve some tasks. For example, I receive a task in real life, then something doesn't work. Then I need to understand what is the business logic of that task. What is basically done, because what doesn't go there. Then I need to represent the task. So I need to take the code. I need to find the place in the code where it happens. I need to launch it, and I need to find the log files or something that proves that it really does those. Because usually in the task it's written example how to launch and how to represent. So you do all the steps and you represent the task. And when you represent, you understand, yes, it doesn't work. Now I need to think where it works. So I need to find the place in the code where, to my opinion, it starts to behave wrongly. Then I just make debug, make the breakpoint, launch it in debug mode. It goes to that place, and then I have to watch what are the values of the variables, what are the values of the object, which objects are created. And very often, for example, you have null pointer exception, so it means that you have something, some value doesn't go, and you just want to use the value that doesn't go, so then you have to figure out why it is. Maybe you cannot read from the database. Maybe in the database there is no object, which is not sent there, and then you need to understand. So this is what the work of the programmer, of the software developer is basically everyday life. Yeah. And, yeah, you have to solve, and you need to be very clever about this, because you need to receive the task, you need to read the task and understand the task. But in order to understand the task, you need to understand what is the application you are making. Because it can be a website, it can be some kind of different application. So you need to understand what does your program do. And then when you do this, then you need to find the place, you need to reproduce the task, you need to find out where the task doesn't behave well, and you need to find it in the code. And sometimes you need to speak with some other more experienced colleagues in order to, if you come to the new job, in order to get the information. Maybe they had already something like that. Yeah. So when I started my job, I always consulted, because it's important to know where it is. And now you see, we are now going step by step. We are using the debugging tools, so you can always debug any code like that. And now we are now we need to understand, we are here, we have executed this line, and after execution of this line, we have generated this object demo. But at the moment you can see the object demo has population size, because we have defined it, population size. Remember, it was somewhere population, where is the pop size? You can see pop size, let me see where it is defined. So if I go to that place, you can see when you define the population, if you go to population class, you can see that pop size is 10. So that's why it's 10 there, because it is defined in population class. And you can see individuals, when you calculate individuals, new individuals 10. So it means that you generate 10 different individuals. The fittest is 0 in the beginning, and then you can go back to your cursor. So you can go back to your to the place. It's usually, you need to remember where you have stopped, where you have started. So here it is somewhere here in the main. Yeah, so here. And you have created the simple J. You see population, individual fittest, second fittest. You just make these individuals, but they are now for now. But now you will make this one. You see here it's even the command. We are going to initialize the population. So we are going to make it, and if you want to see what is inside this function, because for example, if after this function you get error, you need to open this function, this method, by pressing Control, holding it, and modifying. And you can see that initialize population. Actually, what does it make? What do you see here? Do you know what is the structure of that? What is there?
For loop.
It is for loop, yeah. And so, and if we start initialize population, we have some input parameter. What is this input parameter? It is size. And in our case, what was the size? Do you remember? It was 10, I think. Yeah, it was 10. So it means that now we have a void individual length. You see, so here, and here we have, actually, I don't understand why in this code is written here size, because we actually don't use even this size here. You can see that here, if you take this size, it is not used. You can see it is not used. So there is no sense of that, yeah. I have taken this code from the internet. Yes, so it's like I was looking for very simple genetic algorithm code, and I found this one. I started, yeah, it works, so I will take that and we will analyze it with you. But here we don't even need this. I don't know why they put it, because you can just neglect it and just make it like that, because you already calculate the individual's length. So you have the individual length, you read it from there. And yeah, so basically you don't need it. And here it would be nice if you have size length, then it would be like the same. And here you can see the individual's I, so we create a new individual. But if we go to individual class, you can see what is being there. You see here is individual, here is random object, and what do you see here? This is also a loop.
Yeah.
And what you see, that individual we have genes length. But now we have to see what is genes. If we have genes, we can see genes. It is the special kind of individual thing, and we just make it the array. Genes is array. How many elements are in this array? 5. You can see it's 5. So it means that how many times will this be made?
So since I is less than genes.length, so we will keep increasing till it is 5.
Yes, yes, and 5 will be not taken.
Yeah.
But it will take 0, so
Because
we'll
it is
take,
indexed
yeah,
0.
yeah, we will take 0, 1, 2,
Till 4.
3, 4,
Yeah.
but altogether there are 5.
5.
Yeah, so we will go through 5 this. And what we do in this, we can create genes. You can see what is genes. If you go to genes, genes is actually, genes is this array, but if we take genes, you see here, and index, what does it mean? We will take certain element of the array. And this element in the array is which? How we calculate it? You can see here genes I means we have math apps. How do you think, what is that?
Math is a
Mathematical,
yes.
yeah, and apps is absolute value. So we'll take it absolute value, so it is like it should be always positive. And what is Rn next in?
Random number.
Random number next integer. It takes any kind of integer what it can take. But after this, you can have it like this. If you for example want to generate what is Rn next, you can just copy this, and here in the evaluation you can always insert. I can copy that, copy. I can insert, and I can execute, and you can see it generates something like that. Yeah, it all the time, when you debug, you have to understand that it is possible to get the intermediate result. But if you write some code here, it will get you intermediate results, taking into account what is present in the memory, because if it is not in the memory, then you cannot use it. But it will not go further to this. And sometimes I was finding one problem, and I was doing the same way, because I came to the place where it is, and I said, now I will just make the additional value instead of that, and then you see it works. So then it means that, but it's really hard. Sometimes I spent 2 or 3 days in order to understand why the task is not happening. It is really sometimes difficult, especially when you start working in different projects. In the new project, you don't know the business logic of the project, how everything is interacted. Yeah, and you are given a just an easy task maybe, but I want to find where this place is, and I think it's there or there or there. Now one can help me because someone is busy, and you see it, and then you try. But I was so happy when I finally found it, But it took me some time, yeah. So, but okay, if you are a junior programmer, you can use, but it's better to solve the task as quicker as it's possible, and so on. So this is a. So this is the following, and you can see this number you get as a random number, but what is this action, this percentage? Do you know? Do you remember from previous lecture what was there? What is this action? Percentage in Java. Who remembers?
Is it mod?
Mod, yes. And what is the action mod? It is like, you see, number mod 2. What does it mean?
Modulus of 2.
It is modulus of 2. But what can we get as the result?
It can be
Okay, let's just try to get, let's just remember that, so we can try to get.
I mean, if we.
If you have, for example, oh sorry, if you have, for example, 95, no 9 mod 2, modulo 2, what result we will get? We need to divide.
Divide 9 by 2 and the rest of the result.
Yes, if we divide 9 by 2, what can be the integer value, the largest we can receive? It is 4. Because if we make 5, it will not work, because 5 times 2 is already 10. But 4 times 2 is 8, so we can have. And then what is the residual?
1.
Residual is 1. So it means that the result of that will be 1.
Yeah.
But if we have, for example, 10 mod 2, what will be the result? It will be 0. You understand why?
Yes.
And so if you make up some number modulo 2, what will you receive?
The residual of.
Either 0 or 1.
Yeah.
You will never receive 4, 5, minus, etc. You will receive only 0 or 1. Do you understand?
Yes.
And this is what we need, because we want to generate the sequence of genes. But
0, 1,
0, yeah, but we want to make them randomly.
Random, yes.
We want to make them randomly. And that it means that we have a 50-50 chance whether we have a random number, we can have 50-50 chance, either 0 or 1. Imagine we're making the first people. Yes, we need to generate. And then we need to generate it like one individual, one bacteria, or what is the specimen, has 5 genes. So we need to take this individual, we need to take how many genes there are, and we need to put it there. Do you understand? And this is done actually here. You can see here set genes randomly for each individual. You can see what is happening. This is basically the small loop, but it creates an individual. And do you understand how it is created? You can see here you have the genes I, and you can see genes I. What is genes once again? So this is the new integer 5. So integer 5 means that you have the array which contains 5 elements. Yes? Understand? And then you can have genes, for example, 1. Then you can have, and you can have each of these elements, yeah? Because you can have each of the elements, and you can have basically here you calculate the individual. But if you have an individual, you can see the individual, it is a new individual, so it has like it also, you create a kind of individual, it is like 10 different individuals, but each individual consists of genes. Do you understand it? Each individual consists of genes, and if you have this one, so then we can see how it is done. So here we can have individual, and you see in individual you have fitness. So each individual has fitness, each has genes, but genes contain 5 different elements. And you can see now, and genes length. And now we can make it, I can make now the next line, you will see how they are generated. You see now individuals are not here, but I will return to the code. I will return to the code. Where is this code? Yeah, here we have the code. You see now I would like to make this line. I will make it now, okay? Maybe I will make it not one by one, but I want to go inside there and go step by step so that you see it is not executed. Because if I execute it, you see, now I will execute it. I press this button. What does it happen? I press this button, look carefully. Here, individuals, you see there are all elements are null. Now I'm pressing, and I have all 10 individuals here, you see? I have all 10 of them, and they are generated. But I want, and you see, these are genes. They look like that. But do you understand that these genes now are randomly generated? Yeah, you saw it in the code. Yeah, and your task is as a software developer. You have to be able to understand, if you are given the task, you need to find that place in the code, and you need to see how it works. You don't need to understand the whole code, because when you work in real life, you will have millions of lines of code. You will never be able to read all of it, but each of you will make a small contribution to the big machine. Yeah, and then if you have a task, for example, the button doesn't work, something like this, then you need to understand, when I press the button, what kind of code is being executed, and then you need to find this place on the code and need to analyze what is happening there, and so on. Yeah, so here this is important. And then here, for example, we can do, I can give you the task, for example. Now we have this generator, but I want to make it so that each individual has not 5 genes but 7. So this is the task. What you need to do, you need to understand where these individuals are generated, and then you need to change it from 5 to 7. Do you understand this? This is a little task, but in order to do this, you need to study the code to get it, etc., and make it so. Yeah. So this is like that. And here you see that here we have the genes which are which are generated here. By the way, we can have such things. We can have such practice afterwards, because it is a real task, like a real software developers have, but it's very primitive, but still the outside. So here we have genes, and you can see that it's randomly generated. Now we can study this one, we can see that one, but if you want, we can return and start it again, and we can make step by step to understand how these loops behave. It is very interesting to see, because then you will understand more of this. So I'm stopping that. If I'm stopping, I can stop, then the program will stop. If I press this one, the program will run and finish. But I can press this one. I don't want to rerun. I need to stop. So I need to stop, and it's enough. So now I will rerun it if I want. You can see I have rerun it. So here we have 13 different. But now I will again debug. I will debug, and it will go again to creation of the random number. Okay, I can basically skip it. Now this one, it's also not interesting, but I want to make this one initialize population. So I want to see what is inside happening. How to make it? You see, I am all the time pressing this button, step over. Step over means just on the same level of code, you just execute one by one. One line, the next line, the next. If you have some kind of method here or function, if you go inside, if you want to go inside this method, because in this method there are always lines of code, then you need to go step into. This is a special button here. So you just press step into, and you are now, you see where you are taken. You are taken to the method initialize population. You see? And you see what you have. You have this. This means you have the population. You can see. And you see now individuals. There are no individuals. Do you see that? No individuals. Now here what you have, pop size you have already, because it is somewhere defined. We already saw it. And now what you will see, you will have individuals. You see, here you are going to make individuals, because initialize population, here you have size. What is the size? It is 10. So you will have 10. But it is somewhere also defined, individuals, lengths, etc. So and then you have to, you see individuals, they are null. But now I'm making not this step into, but I'm making again step over, because I just need to execute. This is the first iteration, so if I execute this, I will have new iteration, and you see, I have here the iteration variable. It is 0, so now we know that it is 0, and we are going to create individuals. You can see elements are null, but now I will create the first individual. So what I will do, I can go to step into, or I can make one. I can make step over for now. Let us make step over. You see, I have one individual, and you see it is generated. But if I want to see exactly how it is generated step by step, I needed to have step over. Yeah, yeah. You can also follow with me if you want. You have this code in Moodle. You can download it. You can open it in the case, and then we can see. We can try to play with this. I think it's the very interesting stuff. And now we will continue. You can parallel, and then we can also have a kind of practice with this. So you see, now we have generated one individual. All the genes are here, but you can see individuals we have only one. What will happen now? I will pressing once again. You see, I now is 1. So if I press once again, I have one more individual. It is also generated. Yeah? And you can see that at the moment, this one is done, then the next one is thing. And now I want to see how the individual is generated. So, because when I press it now like this, it already gives me the next individual in this form. So I have all of this. But I want to see how it is generated step by step. So I can press here one more time step into, like this. I'm pressing step into, and I went into this place, you see, which I showed you before, individual, random, and here we have those genes, and you can see that here we have this expression. Remember we was discussing that with you. So now you are taking here, step by step. And you make it, you see here you have this. You have at the moment individual, you went into individual thing, so you don't know what's happening around, and you cannot, you can press, for example, here individual 0. You can try to call it, but you can see it doesn't understand it, because you are out of that class, and you are in this class, and in this class you don't have something. And this means that now you have to move forward, you have to move here, and you see now you have fitness. For individual, you can see you have fitness you have. But genes you are defined now, but genes are still not defined. Let me try to see that. You see fitness is 0, and now these genes, look, now genes are null. If I press it, what will happen? You have genes in the right form, but they all are zeros. You can see you have generated here by executing this one, you already generated the array of 5 elements. Yeah, because you have defined the finite array. You understand it, yeah? You have defined the finite array. Remember we were talking with you during one of the classes that in Java there is static arrays and dynamic arrays. Yeah, and the static arrays are this, but in dynamic arrays we can use streams or this array lists in order to make a dynamic array. What is the difference between a static array and dynamic array? Maybe you don't remember. It's like a data structure question, yeah? So static array always has fixed size. Yeah, so you see here it's static. We defined already in the place that it has 5 positions. It means that the memory will be reserved for this, even if you haven't filled it, but you will have zeros then there or something. But the memory will be reserved. But sometimes it is so that you have to read some kind of values into the stack, but you don't know how many there will be. For example, you are creating a web browser, and the person is browsing web pages. Firstly, you browsed one page, then you went to another page, then you went to another, and you have the button back, so you can return back all the time. So when you browsed one page, you have to keep it somewhere in a history. So if you make a static array, you can create here like 100, and then you will be limited to 100 web pages which you can browse. Then you will make 101. Then this page either will not be recorded or the last one will be lost. Do you understand? Yes. But also it means that as soon as you start browsing, your memory already will be fully reserved. 100 positions will be reserved. But even if you don't browse 100 pages, you will reserve a lot of memory for those pages, and this is bad. But if you make a dynamic array for that, so it means that as soon as you have one page, it makes in the memory only for one page. Then you can have another page, you can add another page, then you can increase the memory. So this is more flexible way to do that, yeah. But you cannot implement it into array like array has static. You have to make the array list, yeah, in Java. In different programming languages, there could be different solutions. I'm talking about Java, as I know Java best, but you can speak about other languages the same. You can find the way how it is done in C++, in C++, in Python, etc. You can find dynamic arrays, definition of dynamic arrays, and static arrays. This is important to understand. And now we have a static array. You can see even here you see this array is like that. And now let us try to go forward. We have defined only the object. If we go forward now here, we go here. You can see we have defined gene length, and now we make this one, and here we came to the loop. And in the loop at the moment we will modify our genes according to the generation algorithm. And we want, remember this one, math apps random number generated. So here now we are going to modify the iteration 0, so the first gene. You see, now we are going to make here I is 0, and random number, you can see random number here, the seed is there, but we don't know what the random number is. And now I will make it, and look, here it will change. You see, it is changed, but gene I, it is gene 0 is 0 for now. And now we make again, you can see, now it is also 0. And here we make again, and you see now it's 1. You see here? So firstly it was generated 0, then it was 0, and now it's 1. Yeah? And then we go forward like this. It's 1 again. And here we go forward, and it's 0. So now the next step, we will go out of the cycle because I is now 4. But if we add I++, it will happen to be larger than the criteria. I will be larger than gene length, because 5 will be larger than 5, strictly larger. And so we will go out. You can see here. You can even take that here. You can take this expression here, for example, and if you are not sure whether you are going to out or not, you can put it here in the evaluation, and you can see it is true. Yeah, but now it is going to be, you see, we went out because we increased I++, and then we went out. Do you understand? And now we have fitness, but we still don't have the fitness because we have to calculate the fitness. And you see, the next thing is the calculate fitness function. So let us try to see whether we go there. You can see now, here we go. And now we haven't still calculated fitness, but at the moment we have only generated. Then we need to calculate the fitness. Do you understand? And it means that now you can generate, generation you can put. And now if you want to not to continue this part because it will generate a lot of things, then we need to make one more thing. We can put another breakpoint in our code. For example, you want to go strictly to another line, then you can create, you see, now where you are somewhere here, initialize the population. But you can put the next breakpoint here, and then you have to make this resume program. You see here, you just make resume program, and it comes to the next breakpoint. This is very useful thing when you make debugging of your programs, because when you debug a lot of programs, sometimes you understood how this part works, but it has a lot of cycles, and if you press all the time, it is very not needed. Yes, you need just to go to another breakpoint. You know, you put another breakpoint, and you just press go there, and you go there. Okay, and here you can see the next thing exactly is the calculation of fitness. Yeah, and what is the calculation of fitness? It is interesting. What do we do when we calculate fitness? Then we need to analyze it, because initially, when you work with real code, you need to understand how it works. You have to be able to take the code, without any description, you can debug it and you will understand how it works. This is a good skill, actually, with the programmer. Eh? And now, let us try to see what is the calculate fitness. Now, I am opening this part, calculate fitness. I am just opening it to larger. So, this is the calculate fitness. This is the small method. Can you explain me how it works? I will put it a little bit higher. No, this is this method. This method, yeah? This is the method. Can you explain me how it works? Here I think it's not really written, because here you just, what you do here?
You just call in the other methods.
Which method?
Calc fitness.
Yeah,
calc fitness.
yeah. But how many times do you call this method? As many times as you have individuals. So you calculate fitness for each individual. Do you see what you can read from this? You calculate fitness for each individual. And now, if you want to study this method, you need to press which button? Control and hold. And now you make like this. So now we have the calculate fitness, and you can see we came to individual class. So we are now calculating fitness for individual. Now, can you please explain how it works? What do we have to do there? Just read it and see, because you know what is genes. Remember what was genes? It was the what was genes? Array of 5. Yeah, very good. Yeah. And now please explain how the fitness is calculated.
You define fitness versus 0, and then
Yeah, it is defined 0 because we don't know. Yeah, but what is the fitness? Can you understand now from this code what is the meaning of fitness? Actually, you should have understood. You can try to see that code and try to understand what is the meaning of that fitness.
fitness could be either 1 or 0.
No, it can be 4, 5 as well.
So if the genes has 1, so the fitness will increase.
Yes. Yes. So what?
So if we have 5 ones, then the fitness is perfect.
Then the fitness will be 5.
Yeah.
But if we have 3 ones, how much will be fitness? 3. Yeah. This is the meaning. So what does fitness do? It basically calculates the good gene.
Yes.
It calculates the amount of good genes. And this one you should see. This is what I want to teach you. Yes. So that you see the loop and you can see what is done. Understandable?
Yeah, we have an if condition, so the code cannot process if until
Yeah.
the condition is
Yeah. This is what we are learning. Yeah, so I give you codes and we try to analyze it, and now you see that this is actually calculating the fitness. So this is nice. So we can go out of that, right? We don't need to care. You understand how it is done. So you see, now this is how you can do. So what do we do now? If we want to understand what happens, we need to go out to the next line. So we need to come to our code, put the breakpoint next to that line. So we need to receive where our code is. So now I will make here the breakpoint. Why? Because if I don't make the breakpoint here, if I continue running the script, I will execute it until the end. But I want to go forward to see what is there. So I'm just finishing this calculations fitness. When I see I finished the calculation of fitness, look what happens. If I say demo, you take population, you take individuals, you take one individual, you have fitness. You take another individual, you have fitness. You take each individual, you will have a fitness. Yeah, that's good. And look what happened. Now you have to see, you have to analyze what is, you see, what is, let us now see what is done in this line. What is done in this line? Just analyze that line which I selected, because we need to execute it.
It just prints.
What it prints? It prints the generation,
Yeah.
but here is generation count.
Yeah.
Can you comment what is generation count? You see it's 0 at the moment. I think it is understandable. So initially we make a generation and we say initially it is 0. And then when it will be next generation, it will be 1, etc. So we can find somewhere generation count, how you can count that. You can see if you press control, you can see count, but here maybe somewhere we will get the generation count plus plus or something, yeah, but
it's not line 27.
yeah, you see,
Yes.
so it's line 07. But okay, so what do we do here as well? What we have this one, generation population fittest. What is fittest? And you can see it is 4. Yeah, so now let us calculate what is that fittest.
The highest individual with good genes.
Yeah, but here it is 0. But they say what is the fittest? It is, you can see here, we can see where it is used, and you can go to the place where, how do you think, which one would be interesting to get? Fittest, you can see this one is interesting to discuss, because here we have to, what is fittest? If we go here, how is it calculated? Fittest is individuals, max fit index fitness, yeah, so here, so basically you calculate get fittest. It is the method, and the method is get fittest. So here, but where this method was used, it is a good question. And at the moment, we are here. So if we have calculate fitness, let us try to see what is there. You see here we have get fittest. We haven't spoken about that, you see, because we already executed, but they know already what is the fittest. And here, if we get fittest, how can you explain how it's calculated? Look, I will open it to you. This is the get fittest, and it opens here. It is the big code here. Can you just have a look and try to figure out what is being done there? Just try to have a look in this, yeah, and try to understand what is happening there. How the get fittest is calculated. Because in our course we need to learn how to read the code mostly, yeah. So that's why I give you a lot of exercises just to explain how the code works, and here we can also try to see what is there.
It iterates through all the individuals.
Yes, it iterates through the individuals.
Their fitness score, and it picks like the highest individual, the best.
Yeah, and here actually this is a good example of how to filter the highest value. Yeah, because you have, and here you can see, but what is, for example, this one? You see max fit, and you see here you have to, when you have some kind of function, you see it's public, individual, and here get fittest, and you have to return something because it's not void. If it were void, you wouldn't return anything, but here you return something. And what do you return here? You can see you return basically what? Fittest, individual's fitness, and return individuals, the clone of that, yes, so here, but if not, then you return like this. Okay, so here you have the fittest. But you can see here max fit index. What is max fit index for, guys? How do you think? What is the meaning of the max fit index?
The lowest.
What is that? Max fit index.
It is equal to our I.
Yeah,
So
it is I, but I is the iteration for what?
for the amount of individual.
For individuals. So,
So I guess that it prevents individual to have fitness more than one per
no,
individual.
no.
Okay.
What is max fit index? You said it correctly that it iterates through individuals, but if you see I is what? I is the actually the identification code of an individual.
Oh yeah.
You see, and then you can see that if conditions fulfill, if max fit is less than max fit is less or equal than individual fitness, then max fit is individual fitness. So max fit will calculate the number of good genes. But what is stored in max fit index?
Which individual has.
Yes, the identification code of individual. It's like your personal code, it's your social security number in the databases. So to understand which one shall we take from the array to make a crossover with. Do you understand? Yeah. And so you see, when you write some kind of code, you can remember not only the value of the array, but you can remember also the index of the array to use it further. Like, for example, if you are making a game and you have a lot of players and you have your gun, you have shoot it, you have made a shot, then you have to create, for example, a cycle which will check whether the bullet can go through any of the players, and then you can say, so if it went to the player, for example, with the iteration number 5, then it means that the player with the code 5 shall lose some health. Yeah, and then it means that you need to remember the code, and to get it from the cycle you need to get this code, and then you have to call the method so which will remove the health from the player. Yeah? So this is like that, and the same happens here. If you scan individuals, you take the first. You have to get the best individual. So initially you think that you have the minimum value. Minimum value is minus infinity. You have something negative. If you want to see what is the minimum value, you can also put in there. You can see this is the minimum value. Basically, this value is the minimum what you can have. And then it means that you have 5 genes. Even if you have 0, you will have it instead of that, because minimum value will always be smaller. But here you have the condition if if max fit, you see max fit now is very small. If max fit is smaller than the individual fitness, individual fitness, it is the each gene. So it is individual fitness, it is like the amount of of good genes. So it could be 0, 1, 2, 3, 4, and 5.
So that if statements will always be true.
In this case, in the first case, yes. In the first case, but after the first case, it could be true or false. Because, for example, you have 10 individuals. If your first individual has 4 good genes, then max fit will become 4, and then you will come to the next iteration. But for example, the next individual has 2 good genes, and then 4 will be not less than 2. Then you will skip. And then you will take the next individual, etc. And all the time you will skip. Yeah? Okay? This is clear. And now we have to stop for a break. Yeah? We have stopped here, where we calculate the fitness and we understand what is fitness. Yeah? So then we have the index and the fitness. Yeah? So let us try to see what happens afterwards. Yeah? So we have calculated the fitness, then we can see other things, because you see we are still on the same line. So now we have to go from here. So the next thing we have to go for this point. So I will put the breakpoint here as well, and I will continue for the next line. Yes? Do you understand why I'm putting the breakpoints here?
Just to continue.
Yeah, just to come to this, because I went somewhere into this place, and then now I'm going to execute this one, and I want to stay here. But you see here I can go forward, and you can see that now you can have the console, and you see generation 0 fittest 4, it is printed. So they made us the generation 0 fittest 4. What does it mean? All the genes are still not the perfect. Yes, so the genome is still not perfect. So we will go to the next generation. And now let's see what happens. Let us analyze what happens here. We have here a cycle. What is the cycle here? You see, here is while, and And what happens in that cycle? It is quite big. I can open it like this. So can you analyze what happens in this cycle? What is the condition and what is while? Do you remember what was while?
While is
It is loop,
yes.
but it is a special loop, yes? There is a special loop, so while...
While the condition it is not met, keep executing the code.
Yes, and now you see the condition is met.
Yes.
It means that if it is met, it goes inside. But if it is not met, it will skip it. But now what does the code check now here basically? What do we check here?
If it is less than 5.
Yeah, what does it mean?
That the genes is not all
Not all of the genes are perfect,
perfect,
yeah?
yes.
Yeah, so somewhere there is 0. Because if all the genes are 5, then it is like that, yeah. Okay, good. So here means that here we have 5, and it means that if we have less than 5 genes, then we have to go some new generation. We have to produce some new generation. What we will do, you see, first line is we increase the generation. Yeah, what is next? We do selection. So when the new generation becomes, then there is selection. So we have to get the best pair. Yeah, we have to get the best pair of specimen, the fittest specimen. So to cross them and to get the best result. So we do selection. After we do selection, we do crossover. So here we will produce a new specimen. Do you understand? And then here we have a mutation possibility. But what do you think here? Here we have if. Can you explain what kind of if is here and why is it needed?
Rn is a random number, right?
Rn is a random number. Any random number which is generated, yes, random number. But next int is like next random number, so that they don't repeat. And here you have mod 7, modulo 7, and then the less than 5. So what does it mean? Why do we need this if? And what is the meaning of that if? How do you think? Online guys, you can also answer, yeah?
Like a random probability.
It is, but what do you mean by random probability? It is connected with the probability, so that it means that what is mutation? It is not always it happens, right? And we have to make it that sometimes mutation can take place, sometimes mutation doesn't take place. And how can we make it using this formula? So what does it mean? If you have next integer, so we have some kind of random number, and we decide modulo 7, what can be the result? If we take a random number divided by 7 and take modulo, do you remember what we can have as the result?
Divided by 7?
Yes. Remember when we did modulo 2,
Yeah.
there was a possibility to have 1 or 0. But now you have modulo 7.
Yeah.
So what kind of outcomes we can expect? 0 can we expect?
Yeah.
1,
Yeah.
2,
Yeah.
3,
Up to 6.
up to 6. So 1, 2, 3, 4, 5 and 0 and 6. And so if we receive, what does it mean? Random number next iteration. So what is the chance of mutation then? Because you can see here we have random next iterations. Here you have divided by 7 less than 5. It means that not all, if we take less than 5, it means that we take any number, we divide it modulo 7, the outcome can be 0, can be 1, can be 2, can be 3, can be 4, can be 5, and can be 6. And here we say if this less than 5. So it means that if it is 6, we will not go for mutation, but in other cases we will go for mutation. So mutation is almost certain. It's quite a lot of probability there. Yeah, do you understand it? So here, by making this, we can regulate the probability. Do you understand the meaning of that? Yeah. And then you see what is the next. Demo add fittest offspring. So we make the offspring from crossover, and we add it to the population. Yeah, because we need to change the population. And you can see then later again it was this was the population calculate fitness, and now what we do again, we make the calculate fitness. So we make calculate fitness and we make the same. These two lines are the same like it were before. Do you see? Yeah. And then this is the cycle. It will go until this condition will be true, false, until it is false. Yeah, and then we will sign and we remember what kind of what will be the generation, what will be the fetus gene, etc. We will just printing out. Do you understand that? Yeah. So actually, by analyzing this, do you get the idea of genetic algorithms? What is the idea of genetic algorithms?
So we keep counting the probabilities until a condition is met.
It's not like counting the probability, because here probability is only if we invoke mutation or not invoke mutation. But we are tending to receive the best result.
Yes.
But what we do, we make evolution. So how do we make evolution? We introduce new specimen, new species to the population. But we have to make the mechanism how we introduce the new species, but we can do it using the genetic algorithm, using the crossover logic. And now, after you understand this, we will look into crossover, we will look into selection, and look into, no, this one is clear, generation count, it's just plus plus. But we have to look into selection and crossover and mutation, and also this, to understand the whole, and that is all basically. This is the whole code. It is not difficult, as you see. You see, it is like, but do you get the idea that initially you have the problem that you have these genes not perfect, but you want to make them perfect, and you can show that using genetic algorithms you can evolutionize, you can evolute to the perfect solution. You will receive old ones. But in real life, it sometimes goes so that you are struggling on one and the same. It's like, imagine in real situation there is not only 5 variables which can change. There could be 10 of them or 20. And then if you use this genome, there is very hard to get all the ones. And then sometimes it goes back, sometimes it goes there. And so it is like the process. Yes, yes. And this kind of algorithms, they sometimes work very well, but sometimes they are staying on one place. And it is important to see. Now I have been to some conferences, people are using those. And people are using those genetic algorithms, for example, using symbolic regression. What is symbolic regression? It means that you can have, you know, mathematical functions. You have operations plus, minus, division, multiplication, putting into power, taking cosine, sine, etc. And it means that if you use symbolic regression, you can imagine that you can create a kind of expression, mathematical expression, using the binary tree. For example, I can show you an example of that, like Excuse me, I have a call. Look, what we have here. You see, we have a formula. This formula, yeah? What is interesting? That you can make it as a binary tree. Remember the binary tree structure? Yeah? Here we take the last action. Last action is plus this one. You take the last action, so this basically becomes here, and this becomes here. Understand? Now, what happens to this? Here you have two summands. You have also the action between them. So you just put minus here, and then you have here is the number, and here you have division. Yes? And then you separate. Do you understand?
Yes.
And here you have this one, 7 cosine and y. So what we basically have, we have a binary tree structure. And the binary tree structure is here, here, here. You can use them as a binary tree. So what is the main node, the next node, the next node, basically you can write it. But you can make it the following. Here, 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 here. These are actions. These are mathematical operations. Plus, minus, power, cosine, sine, etc. What we can do? We can leave the numbers to their leaves. Leaves are the numbers and the nodes are the actions. And using genetic algorithms, we can make different substitutions. What if instead of plus we put minus? What if instead of minus we put multiplication? Instead of cosine we put sine. Instead of multiplication we put sine, etc. Do you understand that? And it means that you have data and you can make different combinations of functions and see whether this function can describe how data change. Do you understand?
Yeah.
And genetic algorithms can create. You can do it. For example, I have been to one workshop with scientists, and one of the scientists, they were in a group. They were getting the satellite images from satellites, and they were processing those images in order to find whether there are marshes. You know, marshes is like the marsh is there, so whether the landscape is different. And they have different functions which can describe whether there is marsh or so, and then they can also use this symbolic regression. They have the formula. They have to find the formula for that, and then they're using genetic algorithms to find the right formula. Understand?
Yes.
Yeah, so this is like interesting way how to make neural networks, machine learning, artificial intelligence, because machine learning has to understand, for example, when you look into the image, you have to determine here is the marsh, here is the different terrain, and you need to figure out how to do that. And they're struggling to do that. They have to have good quality image, and then they have to figure it out. So to make this is good for some kind of construction works or some kind of planning of land division, etc. So this is maybe for military purposes also nowadays. And these are the things that you can use also in the genetic algorithms. Yes. So, and I was trying to make it as more simple, because when you look yourself into those things, they are very heavy mathematically. But let us try to finish this genetic algorithm by watching this selection, etc., and then we will try to see. So let us try to see how selection is done. Here is the selection. How can you comment what is that here? You see, what it is simple. Selection, you just make. You have to select two, and you have to take the fittest candidate. And if we take the fittest, there should be the second fittest. So let us now analyze how we take the fittest candidate. Yeah. So control, etc. So here you have get fittest. This is that. Do you remember we were talking about it? So we go back and let us go to the get fittest. We can go like this, and we can make here which was this fittest. This was that one. And now let us say get second fittest. This one you can analyze. What is different here, how to get the second fittest. Let us look here. Just you see, the fittest was above, but now you have to get the second fittest. What is the solved here? Try to analyze that code.
It compares between individuals' fitness. In case an individual and the index's individual fitness is greater than max fit 1, which is 0.
Mm-hmm.
We substitute max fit 2 to be 0 and max fit 1 to be the index.
You see, they want to find the fittest one, and they compare the fitness. So the max fit one was 0s, yes?
Yes.
And then we are trying to find it with the first one, basically.
Yeah.
We compare it with the first one. And if we compare it with the first one and it's larger than the first one, so it's better, then we get this one becomes this one.
Yes.
Yeah,
And
and
this
this
one becomes
one becomes high, so just like that. But if it's different, if this one is larger than max fit 2, then it is like just I.
Yeah.
Yeah? So we have the second fittest. Okay, so this is clear. And everyone understands. Yeah. And now we can do, you see, selection is clear. So in the selection, finally, we have two ways. We calculate what is fittest, what is the second fittest. Let us try to make it. So here if we put selection, here we have the selection, and now we have to start. So we can go here. We can go here. This way. We now make a generation count, and here let us try to make if we know fittest. We don't know fittest. And second fittest, to see if we get selection, we have to know fittest and the second fittest. And if we have second fittest, we don't know that. So then after this, we can go for generation count. We have done generation count. Now we do the selection. So I made the selection, and look, you see, now if I made the selection, I have to have, but it is not there still. And fittest, no, it's not there. It's still, it is there inside, but yeah, of course, because we need to have fittest demo. We make like this, and then we take fittest. Do you see? Because it is attached to the object. Do you understand? And you can see the result is 4. If you take second fittest, then the result will be also 4. So they are all together. They are the same. How can it be? Let us try to see what we have the population. Individuals, this is 3. This is 4. This is 2. This is 2. Here is 2. Ah, it's not like that. We have it is like fittest. It is not the, it is fitness 4, but we don't know which is order. Yeah, but let us try to see. Fittest is like that, and what is the fittest? Fittest is, it is the same or not? Let us try to see what is the fittest. And here, almost the same, yeah. But let us see the how to say demo. How was it? it was here, if we get the fittest population, it was max fit 1 and max fit 2, yes?
Yeah.
Let us try to receive that one. So demo population max, you have to have get fittest, and then fitness. No, fitness is okay, but what is index we need to take, yeah? Genes. Let us take genes. You see, this is the genes. And if we say get second fittest genes, the same. They take the same. But we can try to see whether maybe we have the same opportunities there. Let us try to see. So we have individuals. So here this the first individual, the fourth, this one. Where are those? Actually, we have 6. This is not. 7 is this one. 8 is not. No, so it is like they all the time take the same, which is strange.
Yeah.
This is strange. So we need to see whether it is like good or bad, because maybe they make it. Maybe it's possible for this version they can be together. Like, you know,
Yeah,
it could be like one person. It's enough to be one and the same to make this. Who knows? It could be possible as well, maybe for them. So okay, we have understood that, and now we need to go from selection. Now let us analyze the crossover. So this is interesting how the crossover is done, and try to explain me how the crossover is done. So here is the crossover. Can you explain me how it is done? What is the principle of crossover? What is the principle of crossover?
Just swaps the value to variables.
Yeah, but you see, there is also interesting thing, crossover point.
Takes a
Just,
random integer out of the population's length.
Individual's length, gene length, I think it's for gene
Yeah.
length. Yeah. So it means that you make a interesting thing. You go just like that, and it means that you fix some value until which you will make a crossover, and the other things will stay the same. Do you see what we did? Yeah. So it is like in order to simulate. It's a question, of course, whether this simulation is very close to the truth, realistic. Yeah.
We're just shuffling them randomly.
Yes, exactly. So that's why if you take the code somewhere, if you don't analyze it, you will never understand whether it's really realistic or not. Yeah. And now you can see, I think it's not really realistic. It's just very simplified. But you need to make it more realistic. Yeah. So this is like you have to figure out how it is done. Then you need to know how it is done in real life, etc. But these are the parameters which you can. By the way, this is a very good topic for diploma paper, for bachelor paper. To take the, for example, to genetic algorithm, and to make research on this, how it works, introduce some other things. This is really like a good research paper, basically for students. Yeah, this could be like for if you want to make a diploma paper, you know. But here, because you can have a lot of different changes, you can say, I do simulation like that, or I do simulation in the other case, and which is faster to go, etc. So this is like understandable. Okay, so this is, and here you can see, this is just swapping. This one you already understand. This is very simple thing. Okay. And now let us analyze the mutation, how mutation is done. Please try to see that here. What can you tell about the mutation?